Today we want to talk about a very, we think, a critical topic, which is portfolio planning, right? How we can take our capital projects and put together a 5-year, 10-year plan that reflects the best combination of projects for an organization. So a little bit of an owner perspective here on project selection and prioritization, shall we? So let's just take a quick look at the capital planning cycle. As far as you may have seen this in maybe a 4-phase diagram or maybe a 5-phase diagram. It usually starts off with identifying needs, right? What are the potential projects? What's the business case behind them? What are the demographics if it's a revenue generating program? So the capital planning cycle, right? So we go through our financial planning processes, and then we go through selection, right, and prioritization, which are the ones we want to do, or that's where we determine what we think, the future of our company, right? I mean, which projects are we going to do? How are we going to develop, or how are we going to grow? How are we going to realize our strategic objectives? Project management, right? So we've selected our projects and we've handed them off for design and execution. And really this is the area of the life cycle that's had maybe the most mature treatment in terms of tools, technologies, and data. Again, mentioning like clustering analyses, trending, predictive analytics coming out of capital projects data. I think people see the value of integrated capital project systems, data warehousing, advanced reporting, notifications, and all of those good things that come with it. Finally, we get to monitor and reporting. How are we doing with our projects? Do the business cases make sense? Do we need to reevaluate them? And we feed that back into the capital planning cycle. So typically we see this as as an annual process, right? There's standards on how to go about and doing this and so forth. But usually it's an annual process, maybe with another bite at the apple on a quarterly basis. But it's hard to get right. It's a difficult process, and it's maybe it hasn't been treated as well in terms of data, technology, and tools as the attention that's been focused on projects for design and execution. So we think that there's really some opportunity here, and that's really at Enstoa what we strive for, is to identify pockets of opportunity where value can be unlocked. We all know the state of the industry when it comes to productivity and and the rest of it. It's not good, right? There's issues in the construction industry, and so we're committed to looking and finding little areas of efficiencies that we can help create, and we think we have something interesting for you today. Now, when it comes to selection and prioritization, a few things to mention. I mean, this is really the chance, right, to realize your company's strategy and vision. It's perhaps one of the most critical activities a company can do, right? I mean, you can execute today, but this is where you have your real plan for tomorrow, where you can really see your vision and you can get that aligned with your projects, right? Your portfolio of projects. But it's a difficult process. I'm curious if how many people here are participating in an annual capital planning cycle? Are there people that have that kind of visibility? Okay, there's 1 hand, 2 hands, 3 hands, 4, 5. Okay, a few. What I've seen is maybe the capital planning processes are maybe a little less mature in the way that they've been implemented. A lot of spreadsheets and files being sent around. There may be hierarchical considerations where you've got divisions and departments all rolling up their needs and their ideas of projects and trying to do their best job to merge and select them, and rolling that back up to a higher level capital planning committee that'll then go ahead and make some changes and push it back down. And the cycle of changes is difficult. Also, what's a little bit difficult is that there's also a changing landscape, right? Some of the assumptions we had yesterday may not be valid today, right? The business cases, the demographics, and what proved the project to be green-lighted in the first place may change. And so keeping an eye on those changes and being able to evaluate and reevaluate projects in a timely fashion is something that we are shooting for. One last thing, I want to mention heuristics, right? Rules of thumb, your gut instinct. It's critically important. It's critically important. We have some algorithms, we have recommendations, we have ideas of what the optimal portfolio would look like for you, but really it's the heuristics. right? It's what do you know is the right thing to do? So we're trying to make a system to be more of a decision support system that can play back and feedback with planners, with owners to help them sort of tailor and refine what their capital plan is. So our argument is that a data-driven decision support system, it will reduce overhead in the planning process. There's a lot of work and rework today. We think that can be limited. We're also helping planners rapidly consider alternatives at the same time. So we're going to allow you to look at more possibilities and make decisions in a more timely fashion. Now, we also want you to make better decisions, of course, as well. And so the way that we go about that is through applying combinatorial optimization techniques and discrete techniques with our integer programming models. And we're going to talk about a little bit of that in detail today. But the idea there is to make sure that we've selected and scheduled the most valuable portfolio for the organization. Also, one thing to note, what do we mean by value? And Michael will talk a little bit about this later. Value can be different, right? Sometimes you realize you have a revenue generating project and you calculate a net present value and you know what it's worth, right? And other times you may be looking at something that's more aligned with strategic objectives, right? Or that's satisfying other goals that aren't necessarily about the economic bottom line, but maybe have some internal benefits or more intangible benefits and aligns with the strategy. We need to do a project. How do we actually evaluate? So we have a couple of different valuation strategies that we'll talk about later as well. So just wanted to point that out. Okay, so portfolio optimization, right? So also another quick question. Anybody have experience with operations research, mixed integer modeling? No? Okay, so it's a field that's been around quite a while. In fact, it's got its roots, like many good things, in early 19th century French mathematics. But really the whole field of operations research was really defined actually here in England. The ideas around linear programming, around understanding being able to solve these kind of complex logistical problems really came out of the industrialization of war. There was a lot of work done on in World War I and then also in World War II, and it was actually it was England that first deployed operations research in being able to optimally deploy a early radar warning system, I think back in the late 1930s. So you may have seen some of this before, even if you haven't studied OR. You may have seen in an MBA class doing some linear programming models. Generally, we're looking at problems that are of this form, right? So we have some objective here, right? We have some minimization or maximization function that's subject to a series of constraints, right? And there's a good example of that over here, if we can take a quick look. So we have here this gray area is basically a region of feasibility, right? These lines, these cuts right here are all constraints. Like maybe we don't, we can't buy too much of this product or invest too much in this area or another. Modeling these as equation gives us what's called an area of feasibility. And it was really in the late 40s and 50s that people developed the simplex algorithm with the insight that the optimal point for such a problem is always on the boundary of the feasibility area. But when it gets to mixed integer models, that's not necessarily the case. Here we can see modern portfolio theory coming around in the 1960s with Markowitz. I really like this picture. I know it's difficult for you to see in the front, but essentially it's a combination of all the potential portfolios of all potential portfolios of investments from investment options, every single combination. And what it did is it took the net present value model and also added the dimension of risk to it, so that you could see the equivalency between a low risk portfolio, a high risk portfolio, and how their expectations are equivalent. So that kind of went into Wall Street and finance and so forth, and into that. But it didn't. It's similar, but it didn't really address scheduling, right? Because when we're talking about project investments, we're not just saying I'm going to buy a certain bond or stock. We're talking about something that's going to take a year, 2, 3, 4, 5. Who knows? They're big commitment investments, and they need to be scheduled appropriately. So what we think of constraints, when you get back to these lines here, are really the different kind of profiles of your organization. It could be your resource loading, what type of resources we have, like cash flow, people, staff, and there's other constraints as well. And we're going to talk about those a little more in detail. I'd like to introduce again Michael Matosin from Enstoa, and maybe you can kind of take it from here on walking us through some of the maths.
Yes, I'm going to take over for a moment. The first thing I'll say is that optimization has been around for a few thousand years. The stuff that we're doing, if you'd like to trace it back, can be traced back to the methods of Isaac Newton and Leibniz, so this stuff isn't new. The particular slice of optimization that we're tackling, as Mike has mentioned, is called integer programming, as we've listed on the slide. It is intimately related with a formulation called linear programming, and the best way to describe those is by looking at that little plot in the middle. So in the middle of that slide with the gray feasibility set, you'll see that there is a little dot that denotes an optimal point. And if you squint your eyes, you'll be able to say that that optimal point is somewhere around 2.8. Now, if anyone in this audience has figured out an effective way to complete 0.8 of a project, please do let me know after the presentation. I would very much like to have a chat with you. In the real world, we can't build 0.8 of a project, complete 1/3 of a warehouse, or deliver 2/5 of a vehicle. We have to complete the whole thing, or we complete nothing. And that is the central use case of integer programming. Integer programs do not allow fractional solutions. If this was an integer program, this middle plot here, you would either get the solution 2 or 3. You would never get that 2.8 range solution. Why is this important? The methods for solving integer programs are significantly different and significantly more complex than other mathematical programs that do allow fractional solutions. They are based on wholly different methods, and it's actually very, very poor practice to take that 2.8 solution and say, well, 2.8 is close to 3, so we should just go ahead with 3 projects because we rounded up. That seems like an intuitive thing to do, but the mathematics underlying the way to get that solution, it turns out that in almost every case, that's actually a very, very bad thing to do, which is why we're presenting the integer program that we have. The future is very bright. I'd say the present is very bright for this kind of mathematical programming for 2 reasons that act in concert together. The first is the global move towards AI and automation. People these days are very comfortable with machines telling them what to do. As much as we hate to admit it, we follow their GPS directions. We let them give us notifications when our favorite things are on. So humans tend to trust computers when we believe they do a good job of telling us things. Similarly, computational power has increased exponentially in the last 10, 15, 20 years. Computers are faster, they have more memory, they can do more calculations per second. Those 2 things acting in concert have increased the theoretical developments in this field, because integer programmings tend to be huge. You can't solve them by hand. You need a computer. And as computers have become more powerful, we could tackle more complex integer programs. And I say we like I've did it, I haven't. Academics have developed very, very efficient and very performant algorithms for precisely these kind of problems we're talking about today in the last 20 years. So it's a very new field. There are a lot of developments, and it's really coming into its own at the moment. First of all, for those of you in the front, you're probably having a tough time seeing. There is a complicated set of equations to the right of this slide. You will all be quizzed on that at the end of this presentation, so please do take notes. Before we get to that, optimization, every integer programming model needs 2 things. Firstly, it needs an objective. What is an objective? An objective is something to optimize. It is something to maximize. Let's think profit or return on investment. Or it is something to minimize. Let's think minimize risk, minimize cost, minimize number of defects. So an objective is the thing you want to optimize. Put technically, it is the thing that lets you discriminate amongst a set of potential solutions. Every project needs one of those. The objective can be tailored to your specific tastes. So we're going to demonstrate a few today, talk about a few. If you have some ideas for an objective or something you value that isn't captured here, do not stress. Objective functions are a very, very flexible formulation and can account for many, many things not mentioned here. Secondly, a good integer programming model absolutely needs constraints. Constraints are a set of conditions that the solution to an integer programming model must satisfy. If the solution does not satisfy one or more of those constraints, it is not a solution. The model will not output it. You will never see it. So these are crucial. The best practice for constraints is having them be real world and data driven. So good constraints capture what's really going on in the problem you face. So the canonical example that I always give is good constraints capture resource limitations. If you have a budget constraint, which you almost always will, a good constraint in an integer programming model will capture that budget constraint, and it will say, you are not allowed to spend more than X many pounds in this period. Or if you have a human resource constraint, as you most likely will as well, it will say, we only have this many hours of FTE, we cannot schedule any more work above that limit. So those constraints capture the real essence of the individual problem the user faces, and constraints are almost always very bespoke. I spend a lot of hours interfacing with clients and users and their representatives, trying to get my head around their business practices so I can write constraints as close as possible to their needs so that the model output is better. Now, that is the background. Now we're going to get into what Enstoa actually does with this information, with this context, with this modeling approach. That set of three equations to the right of your screen defines what we've called the net present value objective function. So we're all on the same page. When I say net present value, I mean a figure that represents the discounted sum of all cash flows in a project. So that's cash inflows and cash outflows over time. That concept is very highly related to the time value of money, the sort of economics finance rule that $1 today is worth more than $1 in the future, because in the interim period you must account for inflation and the fact that you could invest that dollar and generate a return in the meantime. So the NPV is closely related to that. If we were to optimize a single project case and we only had a single project's NPV to consider, the answer would be very simple. It would be schedule that project as soon as possible so we can start generating a return as soon as possible, because getting a return sooner is better than getting that same return later. That becomes much more complex when we consider more than one project, when we consider 10 projects, 50 projects, 1,000, 2,000, 5,000 projects. It does not become so obvious when you have to do which project, because there are a lot of interrelationships, there's a lot of opportunity cost. If you schedule one project, it binds up resources, so you may not necessarily be able to schedule another high-value project. The central insight of the integer programming model that Enstoa has built, the reason why we're presenting this, is because the model we've built, that includes a set of equations and many, many others, allows you to do two things at once. It allows you to select the best projects to do over a given time horizon. That time horizon can be as long or as short as you like. And then it also allows you to schedule those projects simultaneously. So the results from the algorithm that we're going to show today not only selects projects, so it not only tells you, user, these are the projects you should do based on the objective you've specified, it also says this is when you should do them. This central insight is what makes our model new. As far as we know, there are no models that do both of those things at the same time.
So what Michael has characterized is our standard, Enstoa standard NPV objective function formulation, but there are also additional objective functions that we support that are built into our algorithm, such as makespan, which you mentioned earlier, and we'll talk a little bit more later, and also project count, doing the most projects that you can, type of a optimization function. And then also, but I want to mention Scorecard, because one of our clients found this particularly interesting, where instead of using a precise NPV formulation, that the value was actually calculated over a number of dimensions. One dimension being a more qualitative assessment on the returns of the investment, other dimensions representing the strategic objectives of the organization. How well does this project, for example, support our plans for growth or our plans for diversification, et cetera. So being able to score projects across across different dimensions actually has been met with some favorable feedback. So I did want to mention that. Thank you.
So with all that said, the fundamental question, or an example of the fundamental question we ask and we solve with this model, is stated on the top left of this slide. And that question boils down to, if I have a time period of 5 years and I have 100 potential projects from which I can choose, which project should I select and how should they be scheduled? This is a very simple problem to state, and I imagine that many of you in the audience tackle problems like this every single day. It turns out to be a highly complex mathematical problem to solve. Fortunately, we at Enstoa believe we've cracked it, which is nice for us, but it actually is a quite complex problem. And it's complex for this reason. Scheduling and selection are simultaneous. They should be solved simultaneously. If you solve them separately, you will, in almost every instance, get a suboptimal outcome. I would like to argue this by way of a thought experiment. So if everyone could imagine, they have a portfolio of 50 projects they have to choose from, and they select 10. On whatever basis you prefer to select projects, you select 10, and then you schedule those 10 projects you've selected to try and finish work as soon as possible. That's a reasonably common way of selecting and scheduling projects. If you were to do it that way, you would have no way of knowing whether, if you tweaked or shuffled the schedule around a little bit, it would be possible to schedule 11 or 12 projects and be better off in terms of value or organizational objectives than you were before, because you didn't consider that alternative when you were selecting projects. So that won't do. We need something more sophisticated than that. Similarly, on the other side of the coin, if you looked at that set of 50 projects and you said, I am going to select the top 10 projects in terms of their individual return on investment, and I'll figure out how to schedule them later, if you did that, you were ignoring the opportunity cost of every given project. For example, one of those 10 you selected may be very resource intensive, and it might bind your organization's resources for 2, 3, 4, 5 years. And it may in fact be better to actually do 4 or 5 smaller projects that are much less resource intensive but lead to a greater aggregate return over the same period. That decision metric of selecting the top 10 doesn't consider that counterfactual. So what I'm trying to establish is that selection and scheduling are so intimately related that they cannot be considered separately. They must be considered together, and that is what our model does. Our model treats them as variables in the same thing, solves for them at the same time, considers all of those hypotheticals, all of those counterfactuals, all of the schedule shuffling, to give the user the single most valuable profile based on their objective. So that can be net present value, that can be strategic objectives, but it will return the single most valuable project schedule of all possible project schedules, which can be millions or billions, because it considers those two things simultaneously. Not to belabor the point, but let's look at this. Hopefully most, if not all of you can see it, this very large 3D plot in the right-hand corner of this slide. On the bottom axis, we see something that says schedule. That goes from 0 to 60. That's in months, so this is a 5-year schedule. And then we see something called project that goes from 0 to 100, and that's just a project number. So we're considering 100 potential projects. So that number doesn't mean too much. And on the vertical axis, we see the objective value. So the higher that value is, the more valuable your portfolio is. So you want to get right up as high as you can, because that means you are getting the best portfolio you can. First thing to note is that each line that's made up of those little circles is a single project. So when you see a line on that 3D plot, that's a single project scheduled in time. 3 things should be apparent from looking at this. Firstly, the projects are unbroken. Each project runs from start to finish in a single block. There is no slack or idleness. That is an assumption we've made in the model for convenience and for demonstration purposes. Should a user have a case where that is not necessary, where they would allow a project to be stretched out, that can be handled very, very easily. We've just made that assumption for demo purposes. Secondly, every distinct color in that 3D plot is a different phase. So within each project, you'll see that the phases run in exactly the same order in every instance. That's very important. We don't want construction occurring before design. And that is important because typically each phase has a distinct cost profile. Construction is much more important than, not much more expensive rather than some of the other phases, design and closeout and feasibility studies. So it's important to have construction phasing. The third and most important thing about this 3D visualization is that at no point when I was developing this specific example did I ever tell the model which projects to do or when to schedule any given project. So the output that you're seeing on that 3D visualization comes purely from the model. I gave it no suggestions. I said, I like this project, pick that. I just said, model, you pick me which ones you think are best. So without any selection or scheduling intervention, this model has given me a solution that in this case generates a net present value of, I think that is either 17 million or 17 billion. I can't really see the zeros from here. So the model selects those things by itself, which is the central point, and it does that in a matter of minutes, and we'll get to that point later. So now we are going to enter the danger zone, and by that I mean I'm going to try a live demonstration. I have been testing this morning, and it has worked this morning, so with some luck it'll work again. And this demonstration, we're going to go bootleg, which is the way I like it. You're going to see the dev environment, not our fancy production environment. So as a minimum, this is a very simple example with only 10 projects. As a minimum, to run the model I just showed you, you need 4, maybe 5 data points. Firstly, well, 6, but some of them are obvious. Firstly, you need a time period. You need to know how long you want to plan for. You tell the model, I want to plan for 1 year, 2 years, 5 years, 10 years, however long you want. Secondly, you need budgets. You need at least some upper limit on how much you're willing to spend. So if you have a good idea of your firm's budgets, throw that in the model will account for that. Secondly, and through the rest of them, you need to have some data on each project. So at a minimum, each project must have a duration, ideally estimates for phase duration, that would be best. And each phase, if specified, must have a cost. So you must have project duration and project cost data, which is reasonably high level data. You don't need a data scientist full-time to get that kind of information. Most people have at least a rough estimate of that reasonably handy. And I've cheated a little bit. In column B, I've put value and I've put some pre-calculated numbers. In reality, that would capture the expected cash flows the user is receiving from a project after completion, and we would work with you to get that number. So that number is a little more complex than just a cell in an Excel file, but it can be input to the model as a single number, and we work with you on the pre-processing side to narrow that number down. So really, this is all you need to run a model. If you want more inputs, the model can handle thousands of different constraints. I have heaps of them in my back pocket ready to go when users have interests in defining project relationships that says if project 1 occurs, then project 3 can't occur because they're supposed to be built on the same plot of land and we can't have 2 buildings on the same plot. So we can include constraints like that. If you want project 7 to finish before February 2022, we can include a constraint for that, and the model will only return a solution with that constraint satisfied. So there are a lot more constraints and a lot more data we can use, but this is a minimum input. That's the data, and this is our very sophisticated dev environment. For those who are interested, this is the input we receive from the API. So for those who may have more of a dev architecture background, it's just a JSON list with all that data we talked about, a JSON object. And essentially, this is not going to take very long if things go well. I run this bad boy, and it's thinking about it, it's thinking about it, it's thinking about it, and it's done. So it gives you the time. That particular problem took 0.2 seconds to solve because it was a very easy problem. I've had this problem solved when I'm not connected to a bunch of stuff in 0.05 seconds, very, very quickly. We'll get to some more benchmarking later. So that problem has now been solved. We have solved the optimal portfolio schedule for these 10 projects right here. And in fact, that schedule looks like this. So this slide is the output for that mathematical function we just ran. And this is a standard format. This is just in Tableau. Our actual user interface looks much nicer, but for this purposes, Tableau will do. What we give you is a list of which projects you should do, when those projects should start, and when those projects should end. And so we give the user a full schedule of what they should do and when, and you'll see here I have very conveniently included the net present value, and in this case, this portfolio generates $17.73 million. I apologize, I should have put pounds, but old habits die hard in that respect. So feel free to deflate that by 30% if you'd like. The rest of the discussion works just the same. Now, I am going to make a very bold assertion that I believe with 100% certainty, and that assertion is this. It is not possible you can spend the rest of your life and the rest of everyone you know's life trying to find a better portfolio schedule than that, and you will never earn even $1 more than 17.73 million. That is the single best portfolio out of the millions of potential portfolios of this problem that you will ever see. I'm trying. That sounds a bit aggressive. I didn't mean it to come across that aggressive. But this is the optimal solution for this problem. Now, we want to hammer this point home a little more subtly by comparing it to a more traditional solution for a similar problem. Now, I'm sure you all have seen, heard of, and experienced scheduling models. A lot of common decision support systems have an auto scheduler. You can press a button, the model automatically schedules what you're interested in doing. That typically is done by an objective called makespan, which is a fancy technical way of saying we want to get projects finished as soon as possible. That's what most schedulers use. Makespan does not consider that simultaneity in project scheduling and selection that I discussed earlier. Makespan only considers schedule. Because of that, when you eyeball these two plots, the first one is the one I showed in the previous slide, the second one is new, you'll see that their schedules are very, very different. And the makespan schedule, which sits at the bottom, is biased in favor of very large projects. So you'll notice that project 4 is very, very large. The makespan solver that wants to minimize schedule time is going to drive that one to start early so it finishes early, which stands to reason. That also means that very short projects, a makespan or a scheduling solver is biased against because they're easy to squeeze in anywhere, so the scheduling model will squeeze it in wherever it fits. It doesn't want to drive it to completion early. The net present value model has no such biases. It simply selects and schedules projects on the basis of value. And we see here that projects 2, 9, 3, and 10 to a lesser extent are very high value projects, especially relatively to project 4. And we know that because and I've checked to make sure, and I've designed this example, but we know that as well by looking at the solution that the net present value model drives them to completion earlier. The net present value model doesn't care that project 4 is a long one. All it cares about is that if you finish projects 2, 3, 9, and 10 early, you earn the most money, so it's going to schedule that. And we see here that the net present value model generates 17.73 million and the scheduling model generates 17.4 million. So just in this 10 project example, there is a $300,000 surplus waiting to happen by using our net present value model. Imagine the surplus you could get if you run this for 100 projects, for 500 projects, for 1,000 projects. That value is in the millions for sure. Finally, so this will be the last you hear of me in my technical stuff, we've done some benchmarks. Currently, this model is implemented live with a client we have, and we did some benchmarks because it's actually implemented as a web service, which is a fancy way of saying is we want these solves to be as close to real time as possible. So you, the user, can sit there and say, hey, I have some projects, I think I have a plan, let's check it with this model. The model's given me a result, maybe I like it, maybe I don't, maybe I'll tweak some things, let's run it again in real time. We do not want this to take hours and days for you to sit there and let an algorithm churn. We want it to be done as soon as possible. To that end, we've benchmarked a huge array of examples. Here, you see examples from 100 to 1,000 projects that are variously mid, easy, and high-level difficulty. If you define your budgets yearly, which is a slightly simpler model and I think a better model, you are almost always guaranteed a solution within 1%, often less than 1%, of the theoretical optimum. So not the practical feasible optimum, the theoretical optimum within 2 minutes. In almost all the examples I've solved, no matter the complexity, within 2 minutes, if you define budgets yearly, you are going to get a result that is within 1% of the theoretical most you could ever earn. In harder models, where you define things monthly, the model becomes exponentially more difficult for reasons I can discuss if anyone has questions. In those cases, you will almost always get a result that's within 2.5 or 2% of the theoretical optimum within 3 to 4 minutes. And you can see there's a bit of a performance dip there because those models are hugely complex. As a final note, there are some models that are not suited to quick solves. It is possible to define models that need hours or days to solve. If that is a particular use case for a user, and we've been discussing some of those, thinking about some of those, we're not necessarily wed to having this model as a web service. We can have it as a standalone product that you can press run on, come back in a day or two, and get a very finely tuned solution for your massively complex problem. So that's the model. Mike's going to wrap up. If you have any technical questions, please come and find me. I'm very tedious, so I like to chat those kind of things.
Thank you, Michael. And just back on these benchmarks, I mean, we see a lot of these numbers, less than a second, less than 10 seconds, less than 20 seconds, less than 4 minutes. These are things that weren't really possible, right? 5 years ago even, right? Processing power, theoretical developments, solver developments, technologies, accelerating. Access to computational speed and resources is becoming, more available every day. So the complexity of problems that we can solve in real time, we think we've kind of hit that critical point where we can have a model that has sufficient complexity, that can be a true assistant, support for the planners. And yet it's not going to take days and weeks to run. Now, as moving forward, I mean, we'll be able to incorporate additional levels of complexity as needed, and still get those similar results as processing power and time and solver algorithms improve over the next 5 years. So decision support, right? So really what we're talking about is sort of a feedback mechanism, right? We're talking about having a planner and we have a machine, right? We have, as Michael mentioned, our 5 or 6 basic minimal inputs. Typically, there's project data coming in that's pulled, that's pulled in from project controls tools or business development tools, et cetera. We pull this data in together for initiating the model. But that first solve is really just a starting point, right? We want to get that information to the planners so that they can take a look and say, well, wait, no, this doesn't make sense. Project 3, we know we're going to need to push that out 3 months, or wait a minute, maybe we should make a little tweak here. We want to be able to provide options and alternatives so that and every time the planner makes a decision like that, the planner may say, okay, well, I like where this project's at, I like where that one's at. Those are kind of getting locked in. Those become almost additional layers of constraints in our model. When they want to push something around earlier, start later, et cetera, these are things that just help refine the algorithm, right? And then once the planner has things how the prioritized projects that the person is concerned with, has those locked in, we rerun, and then we can see the best way to schedule the remainder of the project. So the planning scenarios can really be developed in real time, right? And we kind of even think about this as in the room. It's in the planning meeting. You've got your team together. You're discussing everything. You run the model, and then you get the results, discuss, adjust, and so forth. So we really think this provides a capability to accelerate the capital planning process. We quickly evaluate alternative and what-if scenarios. I think we've kind of discussed that, but also by loosening certain constraints and doing some additional type of optimization runs, we can kind of say, well, what if you had $1 more? Could you do, what difference would that make? What would be that marginal, benefit for additional investment in resources, whether that's budget, materials, staffing, et cetera. So we find this as a collaborative tool, a way to communicate between the mental models of the subject matter experts in the capital planning organization and with the mathematical models that we've developed, a way to be able to feedback these deterministic, algorithmic results with the heuristic insights of the planner. So the key takeaways is we think that this helps a company maintain or develop a competitive advantage. As we mentioned earlier, capital planning is the place, that's the moment where the strategy, the future plan and vision of a company is realized. And by being able to have faster decisions, better decisions, and in more timely decision cycles, we think that that's going to put you in a more advantageous position when it comes to your organization's capabilities. Human input, key takeaways, is vital. We're not looking at all to replace or try to circumvent capital planning processes. In fact, we're just trying to make it easier for people to do their job well. And we think that this will unlock a lot of value for organizations. We've gotten some favorable feedback already. As we mentioned, we've deployed this as sort of a beta launch with one of our clients, but we've developed it as an API, so maybe that this can be offered as a service and so forth. So we've encapsulated this. We think it's a strong model, and we're happy to share it with you all. So with that, I'll say thank you and ask if there are any questions. All right.
Can you build risk into the projects that you've got? Because obviously being certain on your schedule and your costs would be fantastic, but that's not real world.
Absolutely. In fact, if we go back to the earlier slide on Markowitz, right? That was where, and that was in I think it was late 50s, early 60s, where risk was really incorporated into these types of models. We haven't incorporated it yet into this model, but it's right there waiting for us. So the question is what kind of risks are we talking about? On the one hand, there's construction risk, right? Risks of execution and delivery, right? But when you're looking at portfolio valuation, what we're really looking for is what is the risk to the business case of the asset, in its delivery phase? How well is it going to deliver on its promise? And so the mechanism there is to understand how construction risk for ongoing projects feeds into that risk of the overall business case of the asset and evaluate that at the portfolio level. So we're prepared to incorporate risk, but we haven't done that quite yet. It's on our to-do list. So thanks for mentioning that.
My short take is yes, risk can be incorporated. There are a few different ways depending on if you have a probability, if you think you have ideas of the probability of risk, or if you have ranges. So for example, if you have a good hunch that your project is going to cost between X and Y, we can actually run the model subsequently, do one solve with it costing X, do one solve with it costing Y, do a bunch in the middle, and get like a sensitivity analysis that way. So we have a few methods.
And final point, when we're looking at risks and how they affect, and project performance and how that affects the overall cost of the project and eventually the business case of the asset, it may be that a project that you greenlighted last year that's not going so well, or some risks have been realized and others identified, it may be the best thing for the organization to put that on hold or kill it for more favorable projects that have come along. So we don't just take the assumption, and it's typically not the case, of course, but we don't just make the assumption when we run our model that any ongoing projects are a given. They have a big leg up on new projects because you've already made that investment and you have a smaller way to go to realize that value of the project. But if there are issues, those actually get pulled into our model as well. So we actually are looking at ongoing and potential new projects together.